Having covered all the topics in finding the derivative using different methods, now we can actually apply those methods to find the derivative of, say, a function or the derivative of a derivative. So what I mean by that is, let's say we have a derivative of function dy dx. We know that this function is going to be a function of x as well, so that means that we should in theory be able to get an expression for the derivative of this derivative. Now the interesting thing about these differential operators is that they're linear, so that means that they can actually be grouped by simply multiplying them together. So this would become d squared y over dx squared. So what this essentially means is that we're taking the second derivative of y, and we will represent this as y double prime x. So this is the shorthand notation for this derivative. So how can we find that? Well, let's say we have the function y equals to 3x squared. So we have y equals 3x squared. Now the first derivative, dy over dx, is going to be 2 times 3, that's 6, times x to the power of 2 minus 1, that's 1. This is our first derivative. Now our second derivative is going to be applied to the first one, so we're going to differentiate this function of x here. So what's the derivative of this function? Well, it's just going to be 6. And if we take a third derivative, so d3 dx cubed, we're going to get 0 because that's just a constant. And obviously after this point it becomes kind of trivial to keep differentiating because all the derivatives higher than 2 are going to be 0. So what we can infer from this is that this can be applied over and over again, and there are functions that will actually continue to come back and forth, and they will have an infinite number of derivatives. So an example of that is the function e to the power of f of x, because we know that once we differentiate this, that becomes e to the power of f of x. This doesn't change at all, but now it becomes multiplied by the derivative of the power. And if we differentiate that again, this is going to be the derivative of this multiplied by that. So that's, and then we're going to have to apply the product rule. So this is going to expand another term, and then the next time we differentiate it, it is going to expand more and more. So in the end, this is just going to become an infinite function, and that's a very interesting thing. But we may have something like, for example, a cosine function or a sine function. So we know the derivative of this is cosine, and the derivative of cosine is minus sine, and the derivative of minus sine has to be minus cosine, and the derivative of this has to be sine of x. So this is going to be going in this cycle forever. So if we start with this function, this would be the first derivative, this would be the second, the third, and the fourth, and after the fourth derivative we have come back to the beginning. So this is going to keep cycling around like that. So that's another example of function that will have infinite derivatives as opposed to this one here. So let's see if we can find the derivatives, the higher order derivatives of a function that is a little bit more complicated than this. So let's have another example. Y equals to 3 times x squared plus e to the power of minus 3x squared plus cosine of 2x. So let's try and find the first 3 derivatives of this function. So the first derivative, y prime, is going to be equal to 6x minus the derivative of this, which is 6x e to the power of minus 3x squared, and the derivative of this is going to be minus 2 sine 2x. Now the second derivative is going to be applied to this, so that's going to be 6 minus, we have, actually it's going to be plus because we have minus 3 minus the derivative of the top, sorry, which is going to be what? It's going to be 6 of 6x again. But remember that we have to apply the product rule here now, because obviously this is a function of 2 functions. So what we can do first is we can have, I'm going to erase this first. we're going to have minus 6 times e to the minus 3x squared. And we're going to have here, what is the derivative of this? That's going to be 6x times minus 6x. So plus 6 times 6 is 40, no, actually it's 36, sorry. Multiplication skills are really bad. 36, and x times x is going to be x squared. So that's going to be our function there. And now we're going to have minus 3 to the power x squared. And for this one, we're going to have now minus 4 cosine of 2x. And we could keep going on and on. So for the third derivative, we will represent this as 3 little dashes there. And then we would get the derivative of this whole thing. But obviously, that means that we would have to use the product rule on this one again and then keep going forth and forth. So in the end, we're going to have a function that is expanding like this. And in general, we can represent the nth derivative in shorthand notation by using this little power between brackets. So this is the same as writing d to the power of n y over dxn. So the nth derivative is just going to be this. And what this tells us is that we're going to take the original function and we're going to differentiate it n times. So each time we differentiate, we're going to take the derivative of the previous derivative and so on and so forth. And this will become useful in later videos when we introduce the geometrical interpretation of the second derivative. And we are going to use it actually to find maximum and minimum values on a function. So for the moment being, this is the most general expression that we have of the nth derivative. In the next video, we're actually going to start talking about the geometrical applications of this and how the first and second derivatives can be used to find local maximum and minimum points on a function.